Okay, let's finish off section 8.6 here in pre-calculus today. One of the previous problems we had done was I gave you the letters M, A, T, H, and I asked you how many different words, how many different combinations could you create out of those four letters? And the answer was that if you think about creating four-letter words, we have four different letters that could be in the first position, three different letters in the second position, two different letters in the third position, and one in the fourth, so there was a total of 24. But what if two of the letters were the same, like in the word pool, P-O-O-L? What if two of the letters were the same, and you switched the position of the two O's, but left the P and the L alone? That would not be a new arrangement. That would not be a new permutation of letters. So how do we take care of a situation where we would have identical letters? All right, and the answer is we have a formula for what are called distinguishable permutations. Distinguishable means, hey, I can tell the difference between that one and that one. And what we do is we take n factorial, where n represents the total number of objects. So in our pool problem, there's four letters altogether, so we take 4 factorial. And then what we do is we divide by any number of things that are identical at a time. So there's only one P, so I guess if we wanted to, we could divide by 1 factorial for the P's, but of course 1 factorial is just 1, doesn't do anything. We could divide by 2 factorial for the O's, which essentially just means we're removing all of the situations where the only thing we do is switch around the O's. And then if you wanted to, you could divide by 1 factorial for the L's, but you wouldn't have to do that. So what we'd end up with then is 24 divided by 2, or 12 different arrangements of letters. Okay? So with this idea, we can then make the problems a little more difficult. So with this distinguishable permutations idea, we could then take the letters maybe in calculus and ask you for the number of distinguishable permutations. Well, in calculus, there's 1, 2, 3, 4, 5, 6, 7, 8 letters altogether. So the total number is 8 factorial. And then what we do is we take any letters that are exactly the same or identical and divide out that number factorial. As an example, there's 2 C's. So we're going to divide by 2 factorial to take care of the situations where all we do is switch around the C's. Well, there's also 2 L's, so we'd have to divide by 2 factorial for the switching around of the L's. And then finally, there's 2 U's, so we divide by 2 factorial to take care of the switching around of just the U's. And when we punch each of these out, 8 factorial, I believe, is 40,320. Each of the 2 factorials is 2. What we'd end up with then is, let's see, 40,320 divided by each of those 2's would then give us 5,040 distinguishable permutations. Or probably an example that every high school or college student does in the US. Let's take the letters of Mississippi and calculate the total number of distinguishable permutations. Okay? What we do is we take the total number of letters, which is 11 factorial, and then we divide by the number of letters that are identical factorial. So as an example, we have 1, 2, 3, 4 I's, so I'm going to divide by 4 factorial for the switching around of the I's. I've got 1, 2, 3, 4 S's, so we divide by 4 factorial to take care of the switching around of the S's. And finally, I have 2 P's, so I divide by 2 factorial to take care of the switching around of just the P's. And when you guys do the arithmetic on this one, 11 factorial divided by 4 factorial divided by 4 factorial and divided by 2 factorial, what we get as a result then is 34,650 distinguishable permutations for the letters in Mississippi. Okay? Alrighty. Let's see. I'm just going to pause this video because I'm going to get a picture ready for you. So I'm just going to pause. You'll feel a break in the video for just 1 second. Be right back. Okay, hope that break wasn't too bad. What I did though, I didn't know how the picture was going to turn out. I have a photo, I think I showed you guys a couple of years ago when we were doing some counting, but I've got a photo from the 1950s that shows it's a class picture of some identical twins from a high school, or I'm sorry, from an elementary school in Pennsylvania, if I remember correctly. And it's kind of interesting because one elementary school in one small town actually had all of these identical twins. The two boys up here, identical. The two blonde boys that kind of look like Bodeckers, if you know any of the Bodecker boys, identical. Two little girls here, identical. The two accountants over here looking identical. The two blonde girls here, kind of like the girls from The Shining, if you know that movie. The two Austin Power boys here. The two nice girls here, all identical twins. And then these two kids are thrown in the picture because they're twins, but they're actually fraternal twins. So the question might be on a problem like this, what is the number of distinguishable permutations? So again, it's going to be the total number, and if you count up everybody, there's actually 16 kids, so the total number would be factorial, and then you divide by the number that are identical, factorial. So the two boys in the button shirts, the two blonde boys that look like Bodeckers, the two little shorter girls, the two boys that look like they're going to be accountants one day, the two girls from The Shining, the two Austin Power boys, and then the two nice little girls in front. Please notice that we wouldn't divide by 2 factorial for these twins, because if they switch spots, we would be able to tell the difference. All right, and so the number of distinguishable permutations then would be 16 factorial divided by 2 factorial, 2 factorial, 2 factorial, over and over and over again. So divided by 2, there we go. And if I punched okay, oh shoot, I hit the wrong button. Sorry about that, guys. Hit the wrong key. There we go. There we go, now we're set to go. So let's see, divide by, there. And so the number of distinguishable permutations would then turn out to be 1, 6, 3, 4, 5, 9, 2, 6, 8, 9, 10, 11. So the number of distinguishable permutations then would be 163,459,260,000. That'd be the number of distinguishable permutations. Okay? And then we're going to finish off this section with one last definition and formula. And our definition is going to be for something called a combination. And you've heard that word, of course, before when we were doing our binomial expansions. And the formula will look real familiar to everybody from section 5. But now the definition. A combination is an unordered arrangement. So a permutation order was important. In a combination, order is not important. So we call it an unordered arrangement. And we're going to have a formula. You already have this written down, but if you want to jot it down one more time, I should say. Let's see, the formula then would be the total number factorial divided by the second value factorial multiplied by the difference of the two factorial. Okay? Now, I had given you some numerical examples back in section 5, so feel free to look back at any of those. But I just want to finish off with, excuse me, I want to finish off with just a couple of examples to show you where you might use or see a combination. Okay, I think we did a problem in the first part of the video that took the number of people in your class. I should have written that down. I think maybe I used 35. If there's 35 people in the junior class, what we already did was we calculated the number of president, vice president, secretary, and treasurers that could possibly be elected. Well, today we're going to do something a little bit different. Instead of number of ways in which we can elect president, vice president, secretary, and treasurer, this time I'm going to ask you, how many ways can we elect a committee of 4 to work on something for prom? All right? So hopefully prom's going to keep going, but how many ways could we elect a committee of 4? Well, with a committee, the order doesn't matter. It doesn't matter if you're first, second, third, or fourth. All of the people have the same responsibilities and power, so it doesn't matter. Therefore, we're going to call it a combination. So we'd be asking you guys for the number of combinations of 35 people selected 4 at a time. Using the formula, that would be 35 factorial divided by 4 factorial times 35 minus 4 factorial. And if we do the subtraction, 35 minus 4 is 31. It then becomes 35 factorial divided by 4 factorial, 31 factorial. And when we punch that out, we would get 52,360. So that's the number of ways in which we could, select a committee of 4 people. Okay? Another real easy example of a combination would be something like this. Instead of a baseball team, we could think of a basketball team. Now in baseball, it was really important. It mattered to Mr. Ivancic who was first, who was second, third, fourth in the batting lineup. But when Mr. McDonald creates a starting lineup, it doesn't really matter who's first, second, third, fourth, fifth, because once the ball goes up, everybody just runs around like crazy anyway. And it doesn't matter who is first, second, third, fourth, fifth. So when we ask, well, how many different combinations of basketball lineups could we have? It's going to be a combination. And let's say on the varsity team this year, I believe we had 14 people on the varsity basketball team. And if you don't know basketball very well, 5 people begin a game. Or in basketball, we use the word start the game. Okay? So the question would be, how many different combinations of the 14 total people could Mr. McDonald choose 5 at a time? So since order doesn't matter, it's going to be a combination. So it's going to be 14 factorial divided by 5 factorial times 14 minus 5 factorial. When I do the subtraction, 14 minus 5 is 9 factorial. And when I punch out the math for everybody, there would be 2,002 different starting lineups that Mr. McDonald could choose. Okay? So that's the end of section 6. And so hopefully now you'd be okay, you'd be all set to take care of the assignment, the 10-pack for section 6. Please keep in mind, feel free to ask me any questions that you have. Try calling or shoot me an email. I've got some folks who look like they're telling me that we can collaborate somehow in real time. If you guys have other ideas, feel free to pass them on to me. I'm willing to give something a try here at school. So let me know. Otherwise, have a great day, and we'll talk to you tomorrow. Bye.